Seems to be working so far. Hello, Juan. How are you? Did you receive my reply about recommendation letter? I probably did, and I will get to it. Don't worry. Don't you worry about a thing. You said we could meet today at 11:30? Shoot. Did I put that on my... Oh, jeez. Maybe I didn't see your reply. Sorry about that. My apologies. We can set up another time. You'll send me another... Okay, thank you. Sorry about that. Ay. I tell you what. I don't even know. I don't even know what's going on. All right, we're gonna get started here. Oh, geez. We gotta update this. Alrighty. Okay, this is a topic that I find very interesting. And it involves looking at systems in a different way. We're going to look at aircraft from the perspective of the modal space. And it's not a physical space. It's kind of an alien space, but it's really the most fundamental space where dynamics lives. And I'll try to explain what I mean by that as we go. So, yeah, we're going to talk about flight modes. Where do they come from? How do we define them? And so on. And we've discussed a couple flight modes. So for longitudinal flight, we have the short period mode. We also have the phugoid mode. And now we're starting to introduce some lateral flight modes. So there's the roll mode. There's the spiral mode. And the Dutch roll mode. And we'll zero in on each of these today. See where they come from. Okay, how exactly did we discover these modes? Like, why is it that there's 2 modes for longitudinal flight, but there's 3 modes for lateral flight? How do we know the motion that corresponds to each of these modes? What does a phugoid look like? What does the short period look like? And what the heck does it mean to be a mode in the first place? Okay, so let's answer this question first. What is a mode? And they're a little bit abstract to think about. But here's a concise definition. It's not the only definition. I would say that modes are linearly independent subsets of the system dynamics. Linearly independent means they're totally distinct from one another. They don't affect one another. They're just totally separate. So, in other words, for linear systems, the system response is fundamentally just a superposition of the responses of the underlying system modes. So, talking about the modes of a system, it's saying behind the scenes, all of the dynamics that we see are actually created by some basic modes that are like distinct characters that don't affect each other. And it's just the most fundamental way of looking at what's going on with a dynamic system. So, and this modal thing, it's happening kind of in a different space than the physical space. So, where these modes exist is in modal coordinates. So, in order to see these underlying modes, we need to transform the system into, you guessed it, modal coordinates. It's a different space, different than physical reality, where you can actually isolate these modes. So, to get to this alien space, it's accomplished with the following transformation. So, let's define like the physical space here on the left. So, we've been using this vector delta x to describe our perturbation dynamics relative to some reference flight condition. And the states of these perturbation dynamics represent physical things. Like it could be the perturbation in speed or pitch angle or roll angle. But it goes back to a physical thing. So these are the perturbation dynamics in physical coordinates. That just means it points back to something you can see or measure in the physical space of reality. That's where we do modeling. Okay. Now, there's also a corresponding modal space. So I'm going to call this delta Z. And these are going to be our perturbation states in modal coordinates. This is where the modes exist. They're totally independent of each other. And to get from the physical space to the modal space, we have this transformation matrix, P. It's not a rotation matrix, so we'll just call it a transformation matrix. And to be specific, we should say it's a modal transformation matrix, because it takes us from the physical space to the modal space. It relates those two spaces to one another. Okay, let's keep breaking down what this means a little bit. I know it's a little abstract. So using this transformation, we can write our linearized longitudinal or lateral dynamics state vector in terms of a modal state vector. So let's take our lateral dynamics. That's what we've been looking at recently. Our lateral dynamics has 4 perturbation states. Delta V, this change in the lateral velocity. Delta P, that's a perturbation in your roll rate. Delta R, it's a perturbation in the yaw rate. And delta Phi, perturbation in bank angle. So these are our lateral perturbation states. And let's just say, once again, this is physical coordinates. And then we're going to have our modal states, And we're gonna just label these Z1, Z2, Z3, Z4. And like each of these, like delta Z1, we might call this our first lateral modal state. And so on and so forth. The second, third, and fourth modal states. And the way to jump between one or the other, we have this transformation matrix P. Okay, so these are the state vectors. Let's write the state dynamics in modal coordinates. So the dynamics are our first order equations. So in state space form, we'll have delta x dot is a times delta x plus b delta u. But now what I'm going to do on the next line is use the transformation into modal coordinates. So delta x dot, if I operate, that's the same as P operating on delta z dot. So that would be the first derivative of each of my modal states. And then this delta x right here, that's the same as P delta z plus B delta U here. Now, if I want to get this derivative term by itself, I have to multiply the left and right hand sides by the inverse of P. All right. So all I did was multiply by the inverse on both sides. And now this matrix, P inverse times A times P, we call this our A matrix, but our modal A matrix, because it's like the A matrix for these modal states. Same here. We'll call this our B matrix, but it's like the modal B matrix. So I have this state space expression. It's the same system, like this is still our lateral dynamics for the aircraft, but it's expressed in a different coordinate system. It's kind of like an alien looking at the system and just seeing the same thing but with a different pair of eyes. Okay, now I mentioned above, there's something special about the dynamics of the system when it's viewed from the perspective of this modal space. So here's a description of this special property. Modes are special because each mode's dynamics are independent of the other modes. And you know, to be a little more specific here, I would probably say modal states are special because each modal state's dynamics are independent of the other modal states. I think that's just a little more specific. So this statement isn't true for our perturbation states in like the physical coordinates. Like delta V, delta P, whatever, they're not independent of each other. If you if you change one of them, it'll affect the other states. That's not so with modal dynamics. Okay, so that means the modal states do not depend on each other in the state dynamics equations. And this leads us to an important mathematical thing. This is only possible if the A matrix in modal coordinates is diagonal. You'll see why this is in a second. So, okay, for example, here's our like state dynamics equations, but delta z, these are our modal states. So we're in the modal space right now. And these dynamics should not depend on each other. Delta z1 should not depend on delta z2. Delta z3 should not depend on that, and so on. And, okay. So the only way this happens is if we have... Okay, we have this 1, 1 element, which is non-zero. But all of these elements have to be 0. So it'll be delta z1 is going to be this am11 element times delta z1 plus 0 times all the other states, because it doesn't depend on the other states. Same here. The second state only depends on the second state. 3, 3, 0... So the chain of logic here is that states in modal states are totally independent of each other in terms of their dynamics. Then it follows that in state space form, this A matrix has to be diagonal. That's the only way mathematically these states won't affect each other. Okay, so say like I'm working with aircraft and I want to discover this special space, this way that I can look at an aircraft in terms of just its modes. So we can discover these modal states for an aircraft or any system if we can find a transformation matrix P that takes us to this space with a diagonal system matrix. So this modal matrix, it's related to the original A matrix by this transformation in this way. So if I can find a matrix P that when I operate on my original A matrix in this way, it creates a diagonal A matrix, then I will know that I found this special modal space. So how do you find that transformation? It turns out the key to this transformation is the eigenvectors of the A matrix. So just to be specific, I'm talking about the one in physical coordinates. So I have an A matrix for, say, a Boeing 747. If I want to go to this modal space, the transformation matrix P is going to depend on the eigenvectors of that A matrix in the physical space. And we'll show you how in just a second. So eigenvectors, excuse me, we're going to show right here why eigenvectors are important for creating this transformation matrix. So eigenvectors are found by solving the eigenvalue problem. So let's write that out. This is the eigenvalue problem. If you have an A matrix, A operating on an eigenvalue, and I put a subscript I because if A is n dimensional, n by n, so for flight dynamics, we're typically dealing with a 4x4 for the longitudinal or lateral dynamics. There's 4 possible eigenvalues as well, or there's just 4 of them. So this is the eigenvalue problem. Oh, what am I doing? This should not be lambda I. This should be the eigenvector. Excuse me. So A operating on an eigenvector, and there's going to be n of those, would be the same as an eigenvalue operating on that eigenvector. And like I said, for I equals 1 all the way up to n, which will be 4 in our case. So that's the ith eigenvector. This is the ith eigenvalue. All right, so we can write this system of n matrix equations. So I'm talking about I 1 through n. For each I, there's a matrix equation here. We can write this in block matrix form. So this is what I mean. So we'll go A. So this is for I equals 1. This is for I equals 2, and all the way up to n. This would be equal to lambda 1 v1. So like these columns correspond to each other. Lambda 2 v2 all the way up to lambda n vn. Now you can write this as, we can pull this A matrix out of the left. V1, V2, all the way up to Vn. And this matrix on the right, you can pull out these eigenvalues. So I have the eigenvectors just side by side in columns. And then if I create a matrix, a diagonal matrix like this, all the way up to lambda n. So this is 0, 0. It's all zeros on the off diagonal terms. So this second line is equal to the line above. And we can call this matrix like a capital V. Notice this matrix right here, it's the same one. It's just all of the eigenvectors side by side. And then this is all of the eigenvalues just arranged on the diagonal, 1 through n. And we'll call that like capital lambda. So if we just write this in terms of the symbols we have, we'll have A times this matrix of eigenvectors is equal to that matrix of eigenvectors times the diagonal matrix of the eigenvalues. And I know this equation kind of looks like hieroglyphics at this point. Okay, you'll see where we're going with this in a second. If I multiply both sides by the inverse of this eigenvector matrix, then I'll be left with this. Once again, this is a diagonal matrix. So I could write this in terms of other variables. P inverse A P equals A M. So what's going on here is I started with the eigenvalue problem, and then I wrote it in this block matrix form. And then I ended up creating an equation that looks like the transformation that I wanted up above. And this transformation matrix, which is equal to the matrix of the eigenvectors, it has the special property that it takes us to this space where this matrix is now diagonal. So what I'm saying is the transformation that we need P that we need to go to the modal space is given by P equals what we called V, which is just a matrix that's the eigenvectors of our original A matrix just stacked side by side. Okay, so via the eigenvalue problem, we have discovered a transformation matrix to act on A and take us to the modal space. And in the modal space AM, it's block diagonal, and it's just the eigenvalues arranged along the diagonal. That's what your modal A matrix is. Okay, so how can you calculate this transformation matrix? In MATLAB, it's really easy to do. So here's the syntax. If I want to get the transformation matrix P, and if I want to see what my A matrix is in this transformed space, all I do, I go into MATLAB, I type this, and I use the eig command of my A matrix. And it'll return these values. Actually, how about we do that right now? Okay, this is a MATLAB code that we made, I can't even remember which day. But the point is, we made this A matrix for the lateral dynamics of the 747. So this is my A matrix. It's 4 by 4, and I just called it A747. Okay, this is in the physical space, and it corresponds to my physical perturbation variables. Let's say I want to go to the modal space. So here we go. P, so this is the transformation matrix. AM is going to be eig of this A matrix, which I called A747 lateral. Let's just do that. So here's P, and here's AM. Each column of this is an eigenvector, V1, V2, V3, V4. And then these are the eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. And notice it's diagonal. And we can test this because AM should be equal to the inverse of P times our A matrix, which is A747 lateral, times P on the other side. And that should give us the same matrix. Yep. Boom. It's beautiful. So MATLAB can take you to the modal space with this one command. Okay. Okay, so now that we can go to the modal space, we can observe the dynamics of each of the modal states. So I'm talking about for lateral dynamics, that's like the Dutch roll modal state, the spiral mode modal state, and so on. But how can I observe the dynamics of just one mode in isolation from the others? So what we're going to do is you simulate the homogeneous response of the modal system where only one modal state has a non-zero initial condition. So this is what I mean. We have our dynamics in the modal space. So this is our state space equation. And when you're doing the homogeneous response of a system, that means that you ignore the input. So I just want this part of the system. So I want to solve for the dynamics of this state space system. We could simulate it in MATLAB, for example. But for my initial conditions, when I'm setting the initial conditions for my modal state, I want to choose those conditions so that only one modal state is non-zero. So I just mean this. Every differential equation, you have to define your initial conditions. Let's say I just want to look at the first modal state. So I could do something like this. And if I wanted to just look at the second modal state, well, I would just make that second term equal to 1 or any other non-zero number. Okay, so you could simulate this system using ODE45, other commands, whatever. But after you calculate the time history of this response in the modal space, you can transform the results back into physical coordinates. So these are the dynamics in physical coordinates. When I run my simulation in the modal coordinates, what I'm going to get is this vector as a function of time, the change in the modal states. And really, because the modal states are independent from each other, if I simulated this initial condition, only this first modal state would ever change. The rest of them would be 0. Okay, but anyways, to transform back into physical coordinates, I take that time series, I multiply it by the transformation matrix P. And that's going to tell me what that mode looks like in the physical space. Okay, so we've been talking very theoretically, but I want to help this sink in a little bit, we're going to apply this technique to the Dutch roll mode from the lateral dynamics equations. So we're going to get into it. So this is our example for the day. Isolating the Dutch roll mode for a Boeing 747. We've been looking at the 747 a little bit. Okay, so what we're going to do, we're going to start with the homogeneous lateral perturbation dynamics for the 747, and this is in physical coordinates right here. So we derived this by linearizing our nonlinear flight dynamics equations about just a level reference flight condition at some constant speed. So we have this A matrix. This is the time derivative of our perturbation states in physical coordinates. All right. And then I'm going to plug in some numbers here. This A matrix, if you plug in the values from our reference flight condition, so basically and you would get these numbers for all of the parameters up above from a table. So I'm plugging in numbers corresponding to our reference flight condition. And, you know, just basic 747 geometry. There's a bunch of inertia terms that show up in these variables up above. And so all of that we can look up in a table and just plug in here. Okay. So in my MATLAB code that I brought up earlier, I think I called this A747 lat. That was just my variable for that A matrix. Okay, so our goal is eventually to figure out what the Dutch roll mode is. So we have to take this to the modal space. So what you do in MATLAB is you use eigenvalue, eigenvector decomposition. And this is the command that I ran earlier today. So I'm just putting these numbers back here. But let's point out a couple things. So this first column is V1, the first eigenvector. This one is V2, V3, and V4. And each of these eigenvectors has a corresponding eigenvalue. Oh, whoops. So this is our first eigenvalue. Second one. Third and fourth. Okay. So in the modal space, given this eigenvalue, eigenvector decomposition, we can write the homogeneous dynamics in the modal space. So what I mean is, instead of using the physical states, we have these modal states. Z1, Z2, Z3, Z4. And the A matrix so okay, well, let's do this. So this is delta Z. This is our modal A matrix. And the diagonal terms are each of the eigenvalues. So this is lambda 1. So I'm just substituting in each of the 4 eigenvalues. Lambda 1, lambda 2, lambda 3, lambda 4. Oops. And you can see each of these states obviously does not depend on each other. Like, if I didn't even want to write this as a matrix, like delta Z1 is just lambda 1 delta Z1. You could write each of these equations independently and integrate them on their own. They're not coupled at all. Okay, so we wanted to look at the Dutch roll mode. So the Dutch roll mode is associated with the complex conjugate roots. So in our case, I mean, it doesn't really matter the order, but MATLAB gave those complex conjugate roots as our first 2 eigenvalues. So the Dutch roll, it's been defined as the complex roots that come up. And no matter what aircraft you're looking at, a fixed wing aircraft should have a pair of complex conjugate roots for its lateral dynamics. So looking at the equations up above, the modal states associated with lambda 1 and lambda 2, well, that's just delta Z1 and delta Z2. That delta looked a little weird. So I'm interested in delta Z1 and delta Z2. All right, now if I want to observe the Dutch roll in isolation from the other modes, we calculate the homogeneous response of our modal system using the following initial condition. So I could either do, I'm going to use this variable sigma here. Sigma is just some real scalar. So I could either have the initial condition place some scalar here in the first position, or I could put it in the second position. Because this would correspond to delta Z1, and this would correspond to delta Z2. So it turns out either of these initial conditions is going to excite the Dutch roll mode. Even though it's interesting. So either initial condition will excite the Dutch roll mode, and the real part of the responses, the response is going to have a real and an imaginary part, but the real is the only thing that we're going to see. The real part of the responses looks identical regardless of the initial condition that you use when transformed back into physical coordinates, and I'll show that to you. Okay, so let's go into MATLAB and do this. So we're going to simulate the response using one of those initial conditions, and I'm going to show you the initial command. The initial command is built specifically to do the homogeneous response of a system. So it's kind of cool. You might have seen it used in dynamic systems. I know Dr. Mook likes to use this command. Okay. So when you use the initial command, you're going to have to define a state space object in MATLAB. And part of that state space object is going to be what we call the output equation. So back in the day when we talked about state space, we mentioned that state space actually has two parts. It has your state dynamics equations and it has your output equations. So so for our modal dynamics, here's our state equation. And I'm just going to do the homogeneous part, so I'm not including the input here. Okay, so state dynamics equation. This is one part of a state space model. Then we also have this output equation that we use the variable y. And this has the C matrix times, I'm going to have it times our states in physical coordinates. Actually, maybe I'll do it this way. I think I like this better. Keep everything in modal. Output equation for state space model. Okay, so when we're simulating our system using the initial command, we're going to have to provide this matrix as well as this matrix. But what do we want this CM matrix to be? It's effectively going to pull out the information that we want to plot. Now, what I'm interested in is what a mode looks like. Actually, no, let's do it this way first. We'll come back to this. Okay, we'll just do this first. We'll do this first. We'll go into MATLAB in a second. We'll play around with it. Okay, but this CM matrix, let's see, delta Z CM P wait, because delta X is related to delta Z by this, right? Oh, so delta Z is P inverse delta X. So P inverse delta X. And this would be C delta X. What I'm trying to get at here is we're going to be simulating the response of the modal states, but eventually we want to see how the modes manifest themselves in the physical space. And the way we're going to do it is we're going to use our selection of the C matrix to transform the modal stuff back into physical coordinates. Okay. Let's go to MATLAB before I dig a deeper hole for myself. Let's go to MATLAB. Okay. So we have this A matrix. Oops. I'm going to put this command back in here. A747 lat. Because I'm going to need this. Okay. So I need to make a state space object for the initial command. Actually, let's do this first. This is the syntax for the initial command. Y, T, Z, initial, state space model. So you give it a state space model. You give it your initial condition. Okay, so this is what we're gonna do, and this Y is gonna be your output, which is based on your output equation, and then these are your states. And I used Z because these will be modal states. So let's define this state space model. We're kind of working backwards. So to make a state space object in MATLAB, you use this SS command. And then you give your A matrix. We're not going to give a B matrix because we're just doing the homogeneous response. We're going to give our C matrix because we need that for this command. And we won't give our D matrix. Okay, so we're going to have our A matrix just by doing this eigenvector decomposition. So we have that. So this is why I was talking about the C matrix. We need this. And I think the first thing I'm going to do is make this an identity matrix of size 4. Now what this is going to do, it's going to say our system outputs are just the states themselves. Because the y is equal to the C matrix times your states. So if I multiply my states by an identity matrix, it just returns my states. So this will give me back modal states as my output. Okay, so I have A matrix, C matrix, I have my state space model. I'm gonna do this, but I need initial conditions. So here we go. Our initial condition, if we're gonna just do the first mode, I'm gonna make this 1, 0, 0, 0. Maybe to make this more clear, I'll call this like Z0. It's my initial value for Z. All right. So this will do everything for the initial condition response, and then what we're going to do is we're going to plot all this stuff after. So I'm going to plot T, Y, we'll do line width 2, we'll turn a grid on, we'll make some axes labels, so this will be time in seconds, and then we'll make a legend. So it'll be delta Z1, and then all of our other states. 4, 3, 2. Because our output matrix is designed to return our states. Okay. Is this going to run? I think so. I don't see any errors. So I'm going to run this, and it should give me a plot. Make this bigger. Unfortunately, the text is really small, but anyways, you see this oscillatory response, right? That corresponds to the modal state Z1. The other 3 states are just 0 the whole time, and they're all right on top of each other. So the point is, like I said, the modal states, their dynamics are totally independent of each other. So even though the first modal state is wobbling around like crazy, it does nothing to the other states. So to prove this to you, let's do a different initial condition. Let's excite the second state instead. This time it's the red line, which is Z2, and only that's going, and the other states are 0. Let's do Z3. This one should not oscillate because the third eigenvalue was purely real. Yeah. So I started the third modal state at 1, and it just kind of decays back to 0. But none of the other states do anything because they're independent. And let's just, for the sake of being complete, let's do the fourth one, which I think is a very slow state. I think it's the spiral mode. Yeah, if you look at the time scale on this, it takes, you know, like 1,000 seconds to decay. Okay, so this is the response of the lateral dynamics, but it's from the perspective of this weird modal space where each state represents a mode of complex dynamics. Why do I say complex? Because when we go back to the physical space, you'll see that one mode actually corresponds to the motion of many other physical states at once, even though in the modal space, it's just one state. Okay, let's go back to the surface really quick here. Okay, let's say instead of, for our outputs, instead of viewing the modal states, what if we want to observe the perturbation states in physical coordinates? Okay, so transforming these modal responses back into physical coordinates. Okay, so by physical coordinates, I mean delta V, delta P, delta R, delta phi. So I want my C matrix to... I want my output to be these guys. So this is delta X. Let's call this my C matrix, but there's no subscript for the M because this is like physical coordinates. Hold on a second. Okay, what I'm going to do here, though, you'll see what I do. This. Shoot, let's copy this. Okay, but now I want to write this in terms of delta Z. So delta X is our P matrix times delta Z. So delta Z1, delta Z2, delta Z3, delta Z4. Now, if I do this, if I call this original C matrix, which is an identity matrix, times P, if I call that CM, this will be a special C matrix because it's going to take whatever my modal response is, but if I multiply it by this, it's going to transform it back into the physical coordinates up above. So I'll get to see what the Dutch roll looks like in terms of all these other coordinates. So, well, we'll do this in MATLAB, but when I do this calculation, oh, geez. C sub M is going to be equal to this. It's going to be like a weird looking matrix. Well, actually, this is just equal to, now that I think about it, wow, I'm dumb. I'm taking the identity matrix times P. So that's just equal to P. Okay. So I'm saying if I use P as my C matrix. Okay, let's do it. Let's do it. Let's do it. Let's do it. Okay, so what I'm going to do, I'm going to say Cm is equal to P. This will give me back physical states as my output, even though I'm just simulating modes by themselves. So, okay, what we're going to do, we're going to go back to simulating the first modal state, which corresponds to the Dutch roll. But now I'm going to change this legend. Because now we're going to be returning physical states, which are, okay, our first one's delta V. Our next physical state is delta P, delta R, and delta phi. Okay. So let's see what the Dutch roll looks like in terms of physical coordinates. And this is what you would actually see a plane doing. Okay. So delta V, actually maybe we can put some units in here too. Like delta V is a speed, and I think our units are feet per second. So this gives some like physical meaning to this. This should be radians per second. Delta R is radians per second. And delta phi is just in radians. Okay, so when I induce a Dutch roll on the aircraft, I see that my lateral speed is changing from side to side. It starts with -1 foot per second, meaning it's like to the left, and then it goes back to the right. So this is already telling me the aircraft is going side to side. The other states, it kind of looks like they're zero, but they're not. If you zoom in, you see that they are moving around. My roll angle is changing. Wait, how about we convert this to degrees? That'll be more interesting. So I got to take... how do I want to do that? Okay, we're going to do this like the slow way. V is Y1 in feet per second. And then I'm going to say P is Y2, but I'm going to convert it to degrees. So I got to do 180 divided by pi. R, it's going to be similar. And then finally, phi, Y4. Okay, so, and then I'm going to do this. I'm going to plot each of those independently. TV, TP, TR, T phi, and now this is going to be in degrees per second, which just, it makes more physical sense when you look at it. Hopefully this works. Just run that. Yeah, okay. Maybe we'll zoom in here a little bit and think about what's going on with the Dutch roll. Okay, so once again, side velocity is in blue. I'm moving side to side in the aircraft feet per second. Delta P, that's my roll. So I have an angular velocity. Yeah, that's my roll rate. Okay, that makes sense. The roll rate is basically the derivative of the roll angle, which is in purple. So the aircraft is banking left and right, very small, like 0.2 degrees, at least for this perturbation that I created. And then the aircraft is also yawing, but not quite as much. So the Dutch roll, it's a combination of yaw, roll, and side-to-side motion. If we had a little more time, we could make an animation of this showing like a little aircraft and how it's actually moving. But if we go to... No, it's not this one. Where's that figure? I'll pull it up really quick. Next book. Yeah. It looks something like this. No! Side-to-side velocity, that's where that side-to-side motion is coming from. You see the aircraft is rolling a little bit, and it's not very obvious from this picture, but the aircraft is also yawing. It's rotating about its vertical axis, so its nose kind of swings a little bit left and right. How about we do a different mode? Oh wait, first I want to show you. So we excited the first modal state, and we got this response. Let's like freeze this in our minds. Okay, actually I'll keep this figure open. We'll suppress this closing thing. Now we're gonna just do the second state and see if I get anything different. And I shouldn't. Okay, so I get this figure compared to this figure. Maybe we'll zoom in a little bit. Like up to 20 seconds. Up to 20 seconds. Okay, so you see it's the same. Whether you do, so that's why they say that pair of complex conjugate roots represents the Dutch roll mode, because you could choose one or the other. And when you transform back into physical coordinates, it's just that one motion. Okay, let's make the third. I think this one's the roll mode. And hopefully it just shows the aircraft rolling. Go. Here's my, in purple. Oh no. In purple, this is the roll angle. As it's rolling, it makes sense. P is the roll rate. So as I'm rolling, there's going to be some rate. And then the yaw rate, look at that. There's like a tiny bit of yaw, like 0.4 degrees per second. And there's a little bit of side velocity as well. So as I roll, as I'm rolling, this is a positive roll angle. So I'm rolling and moving to the side a little bit. But yeah, physically, that's what's going on here. Excuse me. And this happens, this is probably too small for you to see, but this happens over a period of like 10 seconds. So this mode dies out really quickly. I introduce a roll angle. The aircraft like moves to the side and corrects its roll angle a little bit. So it's a stable roll mode. Okay, let's excite. Oh, I made that 3. Whatever. This last one should be the spiral mode. So I expect the. What do I expect? I expect the yaw rate to change. All right, let's just run it. Interesting. Oh, first, notice that the time scale on this, it takes like 600 seconds for everything to kind of come down. Whereas the other mode happened in 10 seconds. It was very fast. This starts with a roll angle at like 10 degrees, and then it slowly corrects itself over like 800 seconds, whatever. And let's see what else is going on here. We have this side velocity that slowly corrects itself. And here's our yaw rate. It's slowly correcting itself. So I think what's happening is the aircraft is in a banked turn where it's rolled. Which way is it rolled? I don't know. I can't remember what positive roll angle means. But it's rolled to one side and it's banking in a turn, and it's slowly flattening out, and the turn is getting a larger and larger radius. If wait, we could probably make this unstable. Do you want to try that? The opposite thing happens if an aircraft has an unstable spiral mode. In that case, the roll angle keeps increasing and the aircraft goes into a tighter and tighter turn and the yaw rate increases. How can I make this unstable? What I could do, I could take the fourth diagonal element, and instead of making it stable, I could make it unstable. So right now it has a negative real part. If I take the negative of that, it's going to become positive. And now it's an unstable spiral mode. Oh, buddy. I got to see this. Uh-oh. Uh-oh. Yeah, this is exponentially exploding. I don't know if you can see the power terms over here. It's going like 10 to the 19th. Oh, jeez. I don't even think... Okay, what if I... But yeah, it went unstable. It went unstable. If you have an aircraft with an unstable spiral mode, it loses altitude. It turns tighter and tighter and tighter on itself with an increasing bank angle, and then you just slam into the ground. So that's no bueno. No bueno. Okay. So, okay, I want to just conclude this. I want to conclude this. A couple closing statements. Okay, this CM matrix that we defined up here transforms the modal response back into the physical space where it means something to us in terms of its aircraft motion. In the modal space, it's just you see one mode just doing its own thing, but until you transform it back into the physical space, you don't know what it's actually going to look like. So here, this one was from the Dutch roll. So what we did is we set the first modal state, Z1. We gave it an initial condition of 1. And so it had some dynamics, but down here you just see the straight line. So our other modal states, delta Z2, delta Z3, delta Z4, always 0. Only excited Z1. And like I said at the beginning, the special thing about modes is that they're totally independent of each other. One does not affect the other. So that's why the other modes did nothing. Then what we did, transform this response to physical coordinates. Now the way you do that, like over here we have our delta Z vector. I multiply that by my transformation matrix P. All P is, it's the eigenvectors of your A matrix stacked side by side. That's going to give me my physical state vector. So when we did that, now we transformed into our physical coordinates, which means something to us. We can see it in physical space. Oh, this is when I had the units in radian per second. So you can't really see some of these. But if you zoom in, all physical states are, maybe I'll say excited by mode 1, which is the Dutch roll. Okay, but maybe this is the last point I'll leave with you. However, the physical states are affected in different proportions. So for the roll mode, the roll angle is affected very much. And maybe the side velocity wasn't affected as much. So what we do when we model these modes, and we did this with the longitudinal states, is we model the modes with a reduced number of states. So if you say, like, for example, the phugoid mode, that mainly affects your longitudinal speed and your pitch angle. So we just modeled the phugoid with those two states. So, but the way that we determine which states are important is by doing the type of analysis we did right here. We looked at the different modes, we looked at how they manifest themselves in physical space, and we looked at the relative proportions of the effect. And that's all I wanted to share with you today. I think modes are really cool because you can apply them not to just aircraft, but anything. Really, anything. Like this type of analysis is used in facial recognition, pattern recognition. Anytime you want to distill something to like its most fundamental components, that's going to be done with some kind of eigenvector analysis. So it's pretty fascinating stuff. What happened to my music? We'll put music back on. But that's it for today. I hope you enjoyed it. I hope you're having a great week. I hope the election's not driving you crazy. I wonder if there's any updates since we started. Looks like Biden gained a little bit. What did he just do? He went up to 248. What did he win? Oh, I think Wisconsin. Maybe that's the new result. Wait, so if Biden gets Michigan and Nevada, then it's over. Because I think that brings him to exactly 270, because he's at 248, so he needs 22. 16 plus 6 is 22. Even if Trump takes Pennsylvania, North Carolina, and Georgia, that's what, 16 plus 31, 51. That'll bring him to 266. So Trump needs to win all three of these and Michigan or Nevada. Maybe if he wins these three in Nevada, he would win. But I don't know. I don't, oh, don't forget Alaska. Oh, Alaska, because that's got, but that only has 3. Nevada's still a toss-up. Nevada's pretty close. Oh my goodness. Okay, so if he gets 3. Wait, does that put him at 269? 20, 15, that's 35, 51, 265 plus 3. I think that puts him at 269. It could be 269, 269. Wait, could it? No, because I think if Biden takes these, he would be 270. So it'd be like 270 to 269. Right? No, okay, if Biden wins Nevada and Michigan, it's very close, but Biden. My mom keeps yelling that at me. I don't know what's going on anymore. Send help. Oh, man. Alright, we're gonna send help, Jordy. Oh, man. Has a chance to flip since most of the votes are left in mail. Oh, that's right, right? Yeah, they're still counting mail-in. Okay. Yeah, I mean, it's close, but I think it's harder for Trump to win, isn't it? Didn't do mail-in before 2020. Oh, I see. They're still getting their system together. Huh. Okay. Yeah, I don't know, dude. We won't know Pennsylvania for a few days. Biden just got Michigan and Maine. Wait, this? It's done? Oh, Maine is 3 Biden, 1 Trump. Oh. That's how it could be. That's how it could be two. Wait. We won't know the mail-ins for a few months. That's usually how long it takes to get my packages. Oh man, that's funny. Okay. Crazy. All right, people. I gotta go head to some office hours. I don't know any of the state's laws, but the federal deadline for official results isn't for more than a month. Yeah. Well, hopefully... I heard something about Pennsylvania might be like Friday. Okay, Aqua has a quick question. Yesterday's announcement said that the midterm grade was posted, but I don't see it on Hub under grades. Really? Same there? Whoa. Did I not post it? Hold on a second here. Are you for real? Did I not upload it? Let's see. Okay, jeez Louise. Okay, I just did it. I guess I had it just ready to go. I guess I didn't press the button. So now it should go. I don't know if you'll see it right away or if it might take a couple minutes or something. Anyways, everybody's doing very well. And I'm very much enjoying this semester with you guys. So thank you very much. And thanks for hanging in there. Wow, it's a beautiful day. And it's like getting warm too. Which I'm very happy about. That it's, I think the next couple days are going to be a little sunnier, a little warmer. What does the old weather app say? Yeah, look at this. Look at this. The rest of the week through Monday, it's like should be like 60s, sunny. Ah, good news. Good news, man. All right, gotta go. See you guys. Have a great evening.